net zero, you mentioned that with Barnaby. Articulate what you think our policy on climate should be and how to navigate energy.
Sure.
Because to me, I look at, coal and the vast quantities that we're sending offshore, the number of coal-fired power stations that are going up in China, and I just think, I don't know, why is this a problem for us to build more coal-fired power stations?
Yeah, good question. Same reason we've got ourselves into a mess with climate change that we did with COVID, because people don't understand mathematics, right? So when people talk about science, what's science? I'll tell you what true science is. It's algorithms that demonstrate cause and effect, right? So the study of epistemology, which is the study of knowledge, is basically, there's three types of it. There's empirical data, there's rationalism, and there's skepticism, right? Empirical data is where you demonstrate cause and effect. Rationalism is where you quantify it, and skepticism is where you come in and order it and say, does this make sense? So let's break down the whole climate change narrative right now. First of all, climate change in itself is yet again another oxymoronic statement. It's a disingenuous tautology. It's like saying, do you believe water's wet? Do you believe the climate changes? Well, of course the climate changes, right? So first of all, they throw that question at you, and it's, do you believe? Right? Well, hang on. Science isn't a religion. It's not something that you believe in. It's something you understand, right? And we do understand it, and it was understood hundreds of years ago. And we'll start off in 1687 with a bloke by the name of Isaac Newton. You might have heard of him, right? He wrote this book called The Mathematical Principles of Natural Philosophy. So physics used to be called natural philosophy before the 19th century, right? He came up with 3 laws of motion. I'll just focus on the third one, which is for every action, there's an equal and opposite reaction. Right, now that largely equates to the first rule of thermodynamics. For every heat's neither created or destroyed, it's just transferred or transformed. They're arguing in climate change that an extra 100 parts per million of carbon dioxide in the atmosphere of molecules is going to heat the entire atmosphere by 1 degree. That's basically what the argument is. So let's break it down. 100 parts per million is 1 part per 10,000. Right, so they're saying 1 extra molecule of gas, CO2, is going to heat up 10,000 surrounding molecules of N2O2. So the atmosphere is made up of 80% nitrogen, more or less, and 20% oxygen. Well, actually a little bit less than that, and there's 1% of a few other things, right? Here's the thing, though. Let's go back to basic physics. For every action, there's an equal opposite reaction. In order for one gas molecule to heat up 10,000 other gas molecules, and assuming the same weight, that molecule, by 1 degree, that molecule has to be 10,000 degrees. Right? Because if you want to transfer energy to these other 10,000 molecules, this thing's got to be 10,000 degrees, right, to make the equal and opposite reaction work. Right? Well, guess what? Do you know what the temperature of the sun is? It's 5,700 degrees. So how can a molecule be 10,000 degrees if to heat 10,000 other molecules by 1.5 degree? Now, CO2 is actually 1.5 times heavier than the average weight of N2O2. So in other words, it's only got to be 6,666 degrees.
So why is the Earth heating up then?
It's not heating up, right? So yet again, go back to the...
Just changing.
Well, so what happens? So what causes heat, right? So temperature, let's go back to temperature. Temperature is a measure of mean molecular momentum or energy, right? So momentum's a function, or energy is a function of mass and velocity. Right, so what increases heat is increased mass, right? So we also know that because through the other thing that he wrote, Isaac Newton, in that book was the universal law of gravitation, right? Which is the product of the mass squared over or the product of the masses together. So the weight of the Earth and the weight of the atmosphere, which is both huge, is over the square of the distance between them, right? So yet again, and we know, and we jump a couple of 100 years forward, a bloke by the name of Albert Einstein in 1905 came up with this special theory of relativity, E equals mc squared. Energy is a function of mass. So it is true. 2 things are true here, right? It's just a question of quantum. It is true that basically CO2 absorbs infrared radiation, but it only absorbs it at 14 microns. So you're familiar with the electromagnetic spectrum, think Pink Floyd's, Dark Side of the Moon, where you've got over here ultraviolet light, visible light, incoming infrared, and then outgoing long-wave radiation. Where CO2 absorbs outgoing long-wave radiation is so far out, it's like throwing, on the energy spectrum, it's like throwing a feather on the lake and expecting to have a tsunami. You're not going to get it, right? So it's true that CO2 absorbs a little bit of energy, but what happens when something heats up? What happens when you boil a jug in the morning and it starts to boil?
Steams.
Steams. right? So we know.
I'm glad I hadn't wandered off then.
Yeah. So when they describe the greenhouse gas effect, that's an oxymoronic statement as well, because hot air rises, it doesn't sink. Right, so and we know that if you go to the equator, the troposphere is 16 kilometres high, and in Antarctica it's 6 kilometres high. So heat doesn't get trapped; it expands.
So why is the average temperature of the Earth rising?
Well, who's told you that?
Hey, don't blame me.
Yeah.
It's quoted all the time. The Weather Bureau says so you're saying the Weather Bureau's in on it?
So okay. There's a bloke called Blair Trin, Trewin. He released a paper in 2018. If you Google that paper and go to page 29, there's a table there, right? And they have changed. So as a result of changing instrumentation, they have done this thing called homogenisation. So of that 1 degree in change in heat, about half a degree or 0.6 of it, 0.6 of a degree has come about through what they call homogenisation. So that is where they've gone and said, the Bureau has gone and said, oh, we don't trust these records from 100 years ago. We're going to estimate what we think they should have been.
Oh, what?
Yeah, absolutely. Now, I've studied, I did statistics in Maths 1.
Hottest day since February 1768.
Yeah, so they'll go and homogenise data, and they'll go and do it based on, the differentiation.
It's not real?
Yeah, no, it's not real. So
what?
So they've admitted this to me in estimates. They at Marble Bar, they did 450 million iterations to the maximum temperature and 250 million iterations to the minimum temperature. And they have to have a supercomputer to do it, and it's so complex no one can audit it, right? But here's the thing, you don't need to. No one is saying that every temperature taken in the last 100 years is accurate, but you don't homogenise the data. What you do is you report it with a margin of error. So you might say, and this is the thing, in the 2011 report into the Bureau of Meteorology, sorry, I'm just pulling this out of my brain from a long time ago, the margin of error was plus or minus half a degree, which just happens to be the degree we're talking about, right? But here's the other thing. They've also changed instrumentation from large Stevenson screens to small Stevenson screens. So ultimately, that's just the box where they put the thermometers in, right? So there was a peer-reviewed study done in Spain, which has got a similar temperature to ourselves, climate conditions to ourselves, that showed the difference between a large Stevenson screen and a small Stevenson screen was also about half a degree, right? So you take the half degree through their homogenisation and a half a degree through, moving around, the various thermometers. So you take the one at Sydney Observatory, right? 100 years ago, there was not that much concrete around it. Now there's a lot more concrete, right? So you get the
factors around the instrumentation.
Yeah, exactly, right? So that most of that 1 degree can be explained by the way they have recorded the data and they've manipulated it, and then through the change in instrumentation. But I need to stress, though, that if you do add carbon dioxide to the atmosphere, you will increase the temperature because you're increasing the weight of the atmosphere. And simply, again, it's basically there is an algorithm that demonstrates cause and effect between pressure and temperature. It's called the ideal gas law, PV equals nRT. Pressure is force over volume. So there's your two V's gone. Force, Newton's second law of motion. Force is mass times acceleration. So yet again, we get mass equals temperature, which is a form of energy, right? That's back to Einstein's 1905, same thing, right? And of course, in 1915, and this is the thing that we all overlook here, he came up with the general theory of relativity. Now, the difference between that and the special theory of relativity was gravity, right? Because they knew when he came up with it that he ignored gravity in 1905 with his special theory of relativity. And he knew this because what the work of Newton had done, and the Arabic scholars like in Bin Lathan in the Book of Optics and stuff. It's really fascinating, the history of science itself. So gravity. So when you throw a ball up in the air, for example, and it comes back down to Earth, when you look at the CSIRO energy budget, they want you to think that that's from the radiation, downwelling radiation of CO2. It's completely absurd. So it's gravity pulling the weight, all those molecules. So. And here's the other thing. If you climb Mount Everest, you're technically 10 kilometres closer to the sun, right? And yet it's negative 30 degrees. And the reason for that is there's fewer molecules up there. There's less mass in the atmosphere, right? If you go into outer space, you could be, you know, 1,000 kilometres closer to the sun. It's literally negative 270 degrees or 2 degrees Kelvin. The reason why it's colder is that there's very few molecules out in space because they're all attracted to those heavy objects, right? So it's actually the relationship between mass, gravity, and it's true that, you know, the incoming radiation will heat things up and then it cools down overnight. But the runaway greenhouse effect they're talking about is complete rubbish.